we're good. I'm going to record this, so I'm going to try to stay within these, between this tick mark and over. Well, I noticed that Tim left behind granola bars, so I'm going to take one, pass it around, yeah, get one. Oh, there's not enough for everybody. So you guys get the granola bars, and I'll just go ahead and have my snack that I brought in. Seems fair. You guys, you don't have to eat that crap.
Well, if you want it.
Feeding us today.
I assume he doesn't want it, but they were just here this morning. Take one, pass it around. And if somebody skipped lecture, then I'll get 10 bits. So, just saying. All right. So I want to talk about the reheat Rankine cycle. So that's a modification of the Rankine cycle. So let's go through, first of all, let's think, what was happening in the Rankine cycle? What were the components of it? What were the devices that we had? Yeah, boiler, condenser, pump, turbine. So let's say we put the boiler here. I better stay in the screen here. So let's say we've got a boiler. Let's say the water, and the working fluid is water. We go in. What comes after the boiler? Turbine. Yep. So that. So we have work out. And then, what else do we have? Condenser. And then what? We have a pump, right? Whatever you want, however you want to draw that. So a pump, condenser, great. If we're talking about an ideal cycle, then there are a whole list of standard assumptions. So maybe we'll talk. I was going to do talk about how to deal with non-ideal cycles. Maybe we'll talk about that here, just briefly, and then I want to go into the reheat Rankine cycle, which is a modification of this. But first off, let's talk about the ideal Rankine. What are the standard assumptions, or the ideal assumptions? Okay, you guys hear that? That's an important one. Wait, hold on. Boiler and condenser, what are they? What's the standard assumption? No. Nope. It has to be ice to something. Sir. Okay. Standard assumptions for boilers and condensers is that there's no pressure drop. The pressure is the same throughout them. That's for boilers, condensers, heaters, cooling tower, evaporators, and a refrigerator. Anything whose only effect or only purpose, we use it for heat exchange, not to perform work or, I don't know, throttling or anything like that, just heat exchange. Okay? We're going to assume these are isobaric. And isobaric means what? Just constant pressure. I know that one you guys all know, but coming up on the final, Let's go over the vocab. All right. So that handles these. That's nice. And then what else? We have to have some sort of, what sort of assumptions can we make about the pump and the turbine? Isentropic. Okay, yeah, that's going to be right. More kind of precisely, we assume that they are reversible. So you can return the propeller blades either way for free, and adiabatic. But if it's reversible adiabatic, that's the same as isentropic. Going back to our discussion of Carnot cycle and those kind of systems, we had that same idea. So for the turbine or the pump, the ideal assumption is going to be it's reversible and adiabatic. Does anyone remember, what does adiabatic mean? Wow. So some of us have learned what that means. What does adiabatic mean? Do we all know that? Awesome. All right. This means the heat is zero. Okay. Putting those together, that's going to imply that the entropy is constant. So we call that, if the entropy is constant, we say that it is isentropic. Okay. Isentropic, not isenthalpic. Right? They sound kind of similar. And I don't usually worry about spelling. If it wasn't important, I wouldn't pay attention to it. This is important, okay? Isentropic, because it is entropy that's constant, as opposed to enthalpy. That's what you would assume if you had a nozzle or diffuser or a different device, okay? So for these, the enthalpy will change in general. It's the entropy that's constant, right? There's one other device. If we had a refrigeration cycle, we wouldn't have, there we would a lot of times talk about a compressor. It would be the same assumption in a compressor. Okay, so turbine, pump, compressor. Okay, all right, so those are our assumptions. For an ideal Rankine cycle, these are the components. You work it all out, and basically, mathematically, to work everything out, first of all, you need to know two numbers for two properties for each state. And what you have to be given is the, basically, you have to be told what's going on at two of the states. And then, since something is held constant as you go through these devices, that you can kind of extend that and build it out, and you know two numbers for everything when you kind of logic your way through it, and you can work out all the numbers out. How do you calculate heat or work for the various devices? We need an equation which relates thermodynamic properties to heat and work, or more precisely, power and heat transfer rate. Okay, so that would be for a closed system. So if I view this as one giant closed system, I could use that one. But what I'm going to do is view these as separate pieces, which are each open, and then Lego those numbers together. So I've got a bunch of open systems, control volume systems. So what's the first law of thermodynamics applied to a control volume system? Remember what that one is? That one's, so that's not in terms of Q and W, that's in terms of Q dot and W dot. It's the time derivative. And that one says that Q dot for each device separately minus W dot, so the heat transfer rate minus the power equals the mass flow rate times, and again, you can apply this formula to the turbine or the condenser or the pump or the boiler. So, all right, what we have is the enthalpy leaving the device at the exit minus the enthalpy at the inlet going in. Did I use E and I, or did I use out before? Do you remember? Just okay. There. Okay. It's leaving. So exit or outlet. All right. All right. And then you also have the change in specific kinetic energy and the change in specific potential energy. But those are all zero for an ideal cycle. They're negligible, so you don't worry about them for an ideal cycle. So you don't have to worry about the changes in kinetic energy or potential energy for the purposes of applying this equation. Why do I use enthalpy and not internal energy? Why is it that I have specific enthalpy here, not specific internal energy? No. What kind of system is this? This is not, so for closed systems, I would have Q minus W equals delta U. But this isn't a closed system. And so when you go from a closed system to an open system, it's the energy, it's not just the energy to have the material, it's the energy to have it and also you have to make room for it because you're pushing stuff in and pulling stuff out all the time. So you're talking about enthalpies, not just internal energies. Okay? So for closed systems, you would have this. For open or control volume systems, in steady state, but that's all we're talking about here. That's what you'd have. Remember all these ideas we had? Yeah, no, nobody remembers it. Wow. All right. So this would have been a couple weeks before Thanksgiving, so a year ago for some of you. 2 years ago for most. All right. Anyways. All right. The punchline then is when we're looking numbers up to get our answers, ultimately what we care about really are the enthalpies. It's all about the enthalpies for these control volume systems. So you need to know two properties at each state, fine, but you need that, so if life is nice, if the world is good, then one of those numbers is just the enthalpy already. But in general, you need to be looking up enthalpies to work out ultimately the heats and works of things. Okay? Just trying to give you a review of things that you should know about control volume systems. Okay. Are there questions about this? Now that I have written it on the board, does that look familiar to you?
Yes.
Okay, got one confirmation. Ben?
I don't see it.
He's still having flashbacks to his test from this morning. All right. The moment equals, does Tim call it moment or torque? Did he talk about what's the difference between moment and torque?
No.
He talked about it, I
He
think, at
didn't
the
even
very,
talk about
very
moments, he
beginning.
I always get confused.
I don't really care.
I don't care either.
I had it fixed in my mind last year. I looked it up. Now I can't remember. I think it's something like, when you look at the contributions from each force separately, you call it a moment, and then when you add them all up, you call it the torque? Something like that? I don't know. Maybe that's wrong. I don't know. It's the same stuff. And I don't know. When I went through it as an undergrad, I think we just always called them torque. I don't remember. All right. Great. So that was a Rankine cycle. Now let's talk about a modified Rankine cycle. Okay. All right. So the modified Rankine cycle is you have the same boiler, but you're paying money to have a big firebox going. So it's basically you're trying to get more out of it, is the idea. So what you do is you take your boiler, water comes out, you go through a turbine, so you get work out, and then rather than cooling it down, and then like you would have for just a Rankine cycle, you basically take your water line, run it into your boiler again, so it exits as steam, you extract work. Depending on the numbers, I think the homework problem, you bring it a little bit into the mixed state, but whatever. You just reheat it back into steam again, and then run it into another turbine. You have work out, so you have W.1 and you have W.2 from the reheat turbine, and then you run it into your cooling, into your condenser. And then into your pump. I'm just going to write P for pump. And then into your boiler. And then back to the first one. All right, so you have one boiler, but you're just going to use it again. And it turns out this will increase the efficiency you can get. Do you remember what the efficiency we had for a Rankine cycle was before? I don't remember what the number was. It all depends on the temperatures and things, but I think you're looking at maybe mid-high 20%, something like that. This one you'll be able to get an efficiency that's over 30, so that's good. So it's a more efficient one. It'll turn out, and then you could ask, what about another one, and another one, and another one? It turns out that the boost you get is less and less and less, and then the most expensive component in this cycle to buy is the turbine. So your expenses are going up, and your efficiency gains are getting less and less and less, and you have to run the numbers to, is it worth doing a third or fourth? I think the answer is almost always no, but you'd want to run the numbers. Okay, so, all right.
Is that why hydroelectric is so efficient, because you have no cost in besides
Yeah, I think so. I mean, I'm not an engineer, I'm not a civil engineer, but yes, I think that's right. You're not paying money for that. You're paying money for the construction and maintenance in that case. Yeah. Same with geothermal, right? You're not paying money for the boiler there. There, the cost is just putting installation and maintenance. In places like Iceland, that makes a lot of sense because you have abundant geothermal heat. It's relatively accessible. There you go. I don't know about, I guess in Hawaii you just don't have need for, you don't have, the weather's perfect anyway. You just open the window and it's fine. I don't know, do you guys know in Hawaii, do they use geothermal for electrical production? Honestly, I don't know. Yeah. Okay. For an ideal reheat Rankine, what are the different assumptions we would make for this one.
Not gonna be the same.
Okay, so what we're gonna assume is that the boiler is isobaric, but now we gotta be a little bit careful. It's isobaric, but that doesn't mean that all these have the same pressure. What it means is during one, kind of on one pipeline, pressure's constant. So let's label the states. I'm going to use, I think, the same numbering scheme that's in your homework. So we're going to label this as state 1 is after the condenser, state 2 is after the pump, 3 is after the boiler the first time, 4, 5, 6, and down to 1. Okay? So let's work through what the ideal assumptions imply for this system. I don't know, I'm not very, it's kind of blurry here, sorry. All right, so what are the assumptions going to imply for states 1 and states 2? What can my assumption about a pump tell me about those? What was the assumption for a pump? Ice in tropic. So we're going to assume at state that the entropy at 1 equals the entropy at 2. What do my ideal assumptions tell me about states 2 and states 3? What's related there? What's the standard assumption across the boiler? Constant pressure. So we're going to assume that the pressure at 2 equals the pressure at 3 after the boiler. What about 3 and 4? How are they connected? 3 and 4. How are they related? Adiabatic and reversible, that's going to be the isentropic. So that's going to be S3 equals S4. What about 4 and 5? They're connected through a boiler. The standard assumption there would be what? The pressure's the same. 4 is pressure at 5. And what about 5 and 6? They're connected by a turbine. Entropy. And 6 to 1, they're connected via a condenser. So what does that tell you? Constant pressure. See, if you can assume it's an ideal cycle, just once you assume that, you don't need very many extra numbers. You can pretty much just sew it up with all these equivalences.
If it's not ideal.
Then we'll talk about that.
Terrible.
Well, it's not. Worst case scenario, yeah, it's a nightmare. To be solvable, if it's just a complete, somebody throws a wrench into your turbine, and then you gotta actually read out numbers and do real work. The goal of a physicist is never to do real work. So instead, what you can do are use efficiencies, not the cycle efficiencies, which are what we've talked about before, but what I'm going to talk about today at the end, called isentropic efficiencies, where basically you say, well, if it was isentropic, this would be true, but if it's not, you basically say that the power out of a turbine is down by, you only get 90% out, and so you work out what that means. Okay, so there's a way to, you basically just quote an efficiency, and then it's not like you actually, it's kind of like you don't directly work with the inefficient case. You calculate it based upon 100% efficiency, and then after the fact kind of have a fudge factor which subtracts off what you didn't get out of it. So, And then there's one more. I think that 1 to 6, and then 1 to 2. No, we got that one. Okay. All right, so those are standard assumptions without knowing anything else. Once you say it's an ideal Rankine cycle, you can make those kind of assumptions. Similarly, if this was an ideal refrigeration cycle, you'd start making analogous assumptions for an evaporator or a radiator or a pump, or, okay, you make similar kinds of assumptions. The only one that we haven't seen is a throttling valve or a nozzle diffuser, and those you just assume the enthalpy is constant. So that's just okay. You just swap this out for something else. Okay? Now, to do more than this, I'm going to give you an actual cycle. And then I want you guys to work in pairs. And I'm going to put my laptop, you know what, I'll probably pause this video, and then after you guys solve it, we'll recap and summarize what you guys find. And then I'll record that on here. Okay. Great. So I'm going to give you guys a problem. I left my book at home or have lost it. So I'm going to use this problem out of a different book. That's okay. So we're going to consider a steam power plant operating in an ideal reheat Rankine cycle, aka this one. It's going to enter, so I should have said this. The first turbine is high pressure. Just because it goes into the same boiler does not mean that the pressure is the same. So the pressure between 2 and 3 is going to be different than the pressure between 4 and 5. So we have a high pressure turbine and a low pressure turbine. Incidentally, that's also why you get less and less work out each time, is because you have less pressure difference to work with. Okay. So, entering the high pressure turbine, so what state would that be? What's the state? 3, right? Entering the high pressure turbine. So at state 3, it is given to us that we are at 15 megapascal and 600 degrees Celsius. Furthermore, it is condensed in the condenser at 10 kilopascal. So, let me say that. At the condenser, it's at 10 kilopascal. So that would be the pressure at state 1. So that's megapascal. Mega means what? Million. Kilos, thousand. So get that right. The moisture content. The moisture content of the steam at the exit of the low pressure turbine is not to exceed 10.4%. What would that actually mean? What's 10.4? The moisture content. So what would that mean? Yeah, that's right. Just want to check that. What the heck? State 6. Really working on state 6. Oh, there we go. Yeah. So, we're gonna assume that the quality at state 6. So, the way they phrase it is they say there's a limit on how much liquid is in there, but we're gonna just say that that means the quality is 0.896. All right, so we assume that we have that. What else do I need to give you? Bum, bum, bum. I think that's all I need to give you. So, the questions are, find A, the pressure at which the steam should be reheated the reheat. So that would be the pressure at 4 or 5. B, find the thermal efficiency, eta, and assume steam is reheated to the inlet temperature. Okay, and assume, it says, assume that the temperature at so there's one other thing. Assume the steam is reheated to the inlet temperature of the high pressure turbine. So they say the inlet, so that's the temperature at 3 and the temperature at 5 are the same. So assume, that's one other thing. Assume the temperature at 3 equals the temperature at 5. That's one other thing. Why'd they put that at the end? All right. So these are the things that we are to find, and you're allowed to assume these facts. Which we know, since they gave us the temperature at 3 is 600, so that's going to be 600 degrees Celsius. So basically, you boil it until it reaches its maximum possible temperature. So you keep it in the boiler long enough to get the most out of the fire you've built. That's the idea. If you could achieve a bigger temperature safely, you would. So that's the best you're going to get.
So it drops in pressure in the first turbine?
Yeah.
And then there's no,
Because you're pulling energy out, and the pressure's
there's
going to
no pump to
Yeah, that's right.
increase
That's
the
right.
pressure.
That's right. Yep. You can figure it out. If you did pump it back up, but presumably the energy cost is just undoes whatever you just did. So, yeah. All right. So I'm going to pause this, and then we'll come back.